Okay, this is the very last chapter. We're going to talk about DC circuits. Um, they're not too bad. It's actually pretty easy. It's kind of like Sudoku, little puzzles. So all these things are going to be. Pop right to this thing. So EMF and terminal voltage. If you have a circuit, you need something to cause the charge to flow. Right. So generators do that. Batteries do that. They offer a potential difference, and this is basically also called EMF, which is electromotive force. So it gives those charges a reason to scooch along from one place to another. So like high potential, low potential, that's what all those things are doing. When you have a battery is basically it's chemicals. It's a redox equation. So reduction, oxidation. There are electrons scooching places. There are cations scooching places. When these things move along, there's a little resistance to that flow, and that creates an internal resistance in your battery. So the actual terminal voltage may be different than what your battery says. So if you have like a 12-volt battery and you start pulling some current from that, the actual voltage, terminal voltage, might be like 11.8 or something, right? That's because there's this little bit of internal resistance. So the equation you're going to use to fiddle around with this is this one here. So VAB, this is your terminal voltage. This equals your IMF, or God, EMF, sorry. I was looking at the I there, minus the current times the internal resistance. So this little r, that's the resistance inside of the battery. So if we actually look at kind of a battery here, right? This is the actual voltage of your battery. That's that fancy looking E here, right? The terminal voltage, the actual potential difference between these two poles here, equals this voltage minus the current times the resistance right here, this little resistance. I'm going to make some other videos where I'm going to work through it, so it'll make a little bit more sense. But for now, I'm going to leave that where it is. All right, the main thing I want to talk about in this is calculating the equivalent resistance when you have resistors in series and in parallel. So first off, what does that mean? What does it mean to be in series, or what does it mean to be parallel? So if you have resistors in series, that means they come one right after the other. So boom, 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 just like this picture here. So this is the diagram. This little thing down here, this is your battery, right? So you have your positive end, you have your negative end. So your conventional flow goes out the positive side, goes through these resistors, bip, 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 and then comes back and ends here. All right, so each one of these resistors will drop the voltage. So this current goes through here, the voltage will drop. The current drops again, going through here, and so on and so forth. All right, so we can still do like V equals IR, Ohm's law, for each one of these things. But the drop here, the drop here, and the drop here, that has to equal your total voltage of the battery. So V equals V1 plus V2 plus V3. And if we go to this next slide here, I know that V1 is IR1, V2, IR2, and so on. What I'm getting at is that your equivalent resistance is actually just the sum of all of your resistors. So when they're in a line like this, you just add them up. So if this is 10, and this is 10, and this is 20, so 10 plus 20 would be 40. So we could have a 40 ohm resistor would be acting the same as those three by themselves. So I can put a 40 ohm resistor into this circuit, and it's going to behave just like these three. So we have this equivalent resistance drawn down here. What's nice is now I can calculate the current, because if I know my voltage, right, and I calculate my equivalent resistance, because it's just the sum, I can now do Ohm's law, V equals IR. I can calculate the current going through here. The current through the equivalent resistor, that's the current through all of these. Right? So once I know the current and I know the resistance, I can calculate the actual voltage drop across each of these resistors. All right, because it's not necessarily the same. Like these could all be different resistors, so they'll all have different voltage drops. All right, so that's series. Parallel. Parallel looks a little crazy. All right, so when you have something in parallel, what that means is your line coming out of your battery splits. There's a fork in the road. All right, this one splits into 3 different paths. All right, splits, and then your current gets split. So the current coming out of here splits. It has 3 different paths to go through, and then it all converges again back here at point B and drops here. There's a couple things that are different about this. On this circuit, the current's the same going through all this stuff. So it's all the same exact current, but there's different voltage drops going across the resistors. When I go to parallel, All right, the current's no longer the same. The current splits. These can all be different. I1 plus I2 plus I3, that will equal I, the total amount. But these can be different from each other. But what is the same is that when I go from point A to point B, that's the voltage. The voltage drop across each of these resistors is exactly the same. So if I know that the current, total current, splits into these three currents, let me see, I can go over here. All right, total current is these three currents, and I know that the current is V over R, right? Ohm's law. The voltage is the same for all these things. So that tells me that 1 over the equivalent resistance is the sum of the reciprocal of each resistance. So each resistor I have. So when I have them all in parallel like that, I can do 1 over R1 plus 1 over R2 plus 1 over R3, put that in my calculator, and then I do 1 over that. That gives me the equivalent resistance that I can put into my drawing over here. And then once I know that, I can do these things. A cool thing about having things in parallel is, like, this is the way your headlights in your car are wired. If one of these burns out, if one of these resistors breaks, like snaps, goes dead, right? That's gone. The other lights will still light up, right? If these are light bulbs, if I have 3 light bulbs in a row in series and one of them burns out, they all go off. They're all toast. There's no more circuit. But when you have them parallel, they're still lit up. So let's see. Basically that. If thinking about these things like water is kind of handy. I like thinking of it as little waterfalls. So when I had the 3 resistors earlier, I think of that like three waterfalls. Like the first resistor, it drops, and there's another resistor, it drops again, another resistor, it drops again. So each one of those resistors is like a little mini waterfall. And this picture that's shown right here, right, you got this big reservoir up top, you got the water on the bottom. They're both dropping the same amount, right? And actually, both tubes are the same size, so the flow through them is the same. But this would be like a parallel circuit, right? So the voltage drop is the same on both of them, but the flow, that's going to depend on the resistance, right? The higher the resistance, actually, the skinnier the tube is going to be. The lower the resistance, the bigger the diameter. But sometimes you think of these things like waterfalls and stuff. It may help you a little smudge. Super important tidbit of information. All right, so resistors that are in series are going to all have the same exact current going through them. When you have resistors in parallel, they're going to have the same voltage drop. We're going to do a lot of these things. We're going to figure out the voltage drop across different parts or get the current through different parts of a circuit. But it's going to come down to Ohm's law, so V equals IR, and remembering these two things. So when they're in series, they're all going to have the same current going through them. When they are in parallel, the voltage drop will be the same across them. All right. Last thing here. So your homework. Page 547, problems 1, 5, 7, and 9. 1, it's a level 1. I'm going to say it's probably the hardest level 1 I've seen in your book. It's crazy. I think I'm just going to make a video of something super similar to problem 1 so that you guys can do problem 1, but it's kind of tricky. It's you end up with 2 equations, 2 unknowns, and solving it's not a level 1. It's funky. But stay tuned. I'll get you a video that'll kind of walk you through something like that. The other 2 or the other 3 problems are pretty self-explanatory, just adding things up if they're a series or parallel. Piece of cake. All right. Catch you in the next video.